Today we will begin Chapter 7, where we will be estimating parameters and determining sample sizes. The first section will be estimating a population proportion. In this section, we will have three things that we will look towards. We will look to finding a point estimate, a way to point towards a sample proportion. We will look to construct a confidence interval given an initial level of confidence. And we will look to determine a sample size if I have a predetermined margin of error I want to fall in between. So let's get started. In these examples, we will be given information about a sample and want to point towards a population statement. And so what we need is we need some estimator from our sample to give us information about a population parameter. This estimate is what we call the point estimate. Our first section will deal with talking about the proportion of the population. And the best point estimate is going to be the proportion of a given sample. And we signify those by p hat being the sample proportion and lowercase p being the proportion of the entire population. Let's look at a quick example of finding this point estimate. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. So we want to find the best point estimate for the proportion of all adults. We want to find a proportion in our sample that can be representative of the entire population. In our problem, we're told that 43% of the sample has a Facebook page. That turns into a proportion of 0.43. That is our point estimate. Our sample proportion is 0.43. This will be the value that we will use as the estimator for our population proportion moving forward. Now that we have an estimate for our parameters, we can move on to constructing confidence intervals. And a confidence interval is just a range or interval of values that we can use to estimate the true value of the population parameter. We abbreviate this confidence interval as CI. And what we're doing is we have a true population proportion. We're using our parameter to estimate it, right? Our population proportion for the population is estimated by the sample. Although these are not quite equal, what we need to do is construct a range of values, a lower bound A and an upper bound B, that somewhere in here we're going to say with some level of confidence the true population proportion should fit into. Finding this lower and upper bound is what the whole method of confidence intervals is all about. And determining them is going to be contingent on the level of confidence we want to have. So let's talk about this confidence level. The confidence level is itself a probability, which we consider to be 1 minus alpha, such as 95% or 0.95. And this is how confident we are that our interval will actually contain the population parameter. And we call this the degree of confidence or the confidence coefficient. This is an unusual way to word things as 1 minus alpha. We can think of alpha as our level of unconfidence, right? If we are 95% confident, that tells us that 0.95 needs to equal 1 minus alpha, right? If we're 95% confident, that means we have a 0.05 level of being unconfident. This value, the unconfidence level, will come into play when finding these confidence intervals. This table shows the relationship between that confidence level and the alpha we were discussing. The three most common confidence levels are 90% confidence, or a 0.9 value, 95% confidence, or a 0.95 value, or being 99% confident, being a 0.99 value. And again, if I'm 90% confident, that means my 1 minus alpha value is 0.9, which makes my uncertainty level, or my alpha, 0.10. And that's what all of these values are. Our unconfidence, if we are, for example, 99% confident, that means we're 1% unconfident, which gives us an alpha level of 0.01. Remember, alpha really is a proportion, not a percentage. So if we're 1% unconfident, that means alpha is 0.01. We have to change the percentage into the proportion. One aspect of confidence intervals that is tricky is how we actually interpret them. So let's look at an example. Suppose that we're trying to estimate where a population proportion will lie, and we get a confidence interval of 0.405 and 0.455, and that corresponds to being 95% confident. The correct way that we will interpret this is that we are 95% confident that our interval does contain the population proportion. That we have a 95% confidence level that the population proportion is actually contained in our constructed interval. Right? There are subtle but different ways of doing this. Right? One incorrect interpretation is that there is a 95% chance that the population proportion will fall between our interval. Right? This is incorrect because the value of p exists before we construct our interval, right? This interpretation is saying p must fit into our interval level, but the correct interpretation above says that we are 95% confident that our interval contains the true population. That is slightly different. Another incorrect way is to talk about sample proportions, right? Wrong way to think about this is 95% of other sample proportions will fall between this, right? Our confidence interval really does nothing about sample proportions. Our confidence interval should tell us where our value of p, the population proportion, should fall. That's really what we're looking to do. One of the cruxes of this method is determining critical values. And we've seen this idea of critical values before, but a critical value is going to be the number on the borderline that separates sample statistics that are significantly high or low from those that are not. The numbers we're looking for is z sub alpha over 2. And this z-score of z sub alpha over 2 has the property that it is that separating point. The way we want to think about this is our alpha, again, is our uncertainty. The problem is when we have an interval of values, if we have some level of uncertainty, we could be uncertain to the right of our interval or uncertain to the left of our interval, right? We could be off somewhere over here or off in our calculations somewhere on the left. What we will assume to make our work easier is that both of these levels contain the exact same level of uncertainty. If our total uncertainty is alpha, I have to split it in half to go to the left and to the right, which is why we consider that area to the right and that area to the left of z sub alpha over 2. That's where this alpha over 2 comes from. Our total uncertainty alpha being split into two values. More specifically, two equal values. So let's look to find our critical value. We want to find the critical value z sub alpha over 2 corresponding to a 95% confidence level. If we remember from our chart, a 95% confidence level gives us an alpha value of 0.05, right? That is our unconfidence level. If I divide that by 2, my alpha over 2 is 0.025. If I look at a standard normal chart, that means that this z-score of alpha over 2 should have an area to the left of 0.025. But we've dealt with this problem before. Finding an area to the right of 0.025 is the same as finding an area to the left of 1 minus 0.025, which will give us a value of 0.9750. So what we have to do is look at our table, find a value whose area is 0.9750. That will be our z-score. So let's look at our standard normal table. Okay, like we said, we're looking for an area in our chart of 0.9750. Here I see I have 0.9850. I want to look around and I see right here gives me that area value of 0.9750. And if I look, I get 0.19 and 0.06, and that tells me my z sub alpha over 2, my critical value, is 1.96. This is the value I will take with us for our critical value when we're looking for 95% confidence. This slide gives us exactly what our thought was. If our confidence level is 95%, that means our unconfidence level, or alpha, is 0.05. When I divide that by 2, I get 0.025. This needs to be the area to the right. Our table gives us area to the left. So to compute that, I compute 1 minus 0.025 and get 0.975, which we found having a z-score of 1.98. Because this is symmetric, and I want to cut my value off to the left and to the right, we also have a negative z-score. That will become less important. The important thing to remember is that is how we find our critical value. We can also get very common critical values, right? This critical value of 1.96 corresponds to a confidence level of 95%. There are other common confidence levels we've said of being 90% confident and 95% confident and 99% confident. Their critical values are listed in the chart below. I want to talk about how we compute this value, this confidence value, this critical value of 1.645, because we should notice that this does not have 2 decimal places. This has 3 decimal places. And that's fairly unusual when dealing with z-scores. Our alpha value, again, was 0.10 for being 95% confident, which gives us an alpha over 2 of being 0.05. That means I have an area to the right of 0.05. But my table tells us areas to the left. So I have to take 1 minus that value, or 0.9500. So to find the critical value that corresponds to an alpha level of zero point 0.1, I have to find the z-score with an area to the left of 0.9500. So let's look at our standard normal table again. Again, looking at our standard normal table, I'm looking for an area of 0.950. And if I look right here, I see I don't actually have a value of 0.950. I have two values that are equally far away. What I will do is I will find the mean of their corresponding z-scores. So the z-score that corresponds to 0.9495 is going to be 1.64. 1.64. The one that corresponds to the one just above is going to be 1.65. I'll find the mean of those two values, and that will give me 1.645. That is how we get a 3 decimal z-score when we don't have an exact area measure and we have two values that are equally far apart. Notice that this is going to happen here, which is why our table has those two different values. If I want an area of 0.995, which corresponds to an alpha value of 0.01, the z-score I get is 2.575. And if we look on our chart, that is exactly the z-score that we get for a 99% confidence level. These are going to be the z-scores that we continue to use throughout this example, throughout this section. So let's move on. The main method of calculation in finding the confidence level is by computing a margin of error, E. And this margin of error will be used to find how much we are off between our population proportion P and our sample proportion P hat. We denote this margin of error by an E. And it is based on the z-score that we compute the critical value that we use given our confidence level of 1 minus alpha. We consider this our maximum error of our estimate. And we can find it by using our critical value and the sample proportions that were given. The formula for margin of error E is going to be z sub alpha over 2, our critical value, times the square root of p hat q hat divided by n. And again, p hat is our sample proportion. Q hat then is going to be 1 minus p hat, kind of the complement of our sample proportion. Now we have everything we need to construct a confidence interval around our population proportion. And that's exactly what we're going to do. To construct our confidence interval, again, we let P be the population proportion, P hat be our sample proportion, N will represent the number of sample values in our sample, E will be our calculated margin of error, and Z sub alpha over 2 will be the z-score or the critical value that separates our significantly high values and significantly low values from our significantly unimportant values. Those same three values that we computed just a few minutes ago. To construct our confidence interval to estimate the population proportion P, we'll take our point estimate P hat and add our margin of error to find our upper point B, and then take our point estimate P and subtract our margin of error to find our lower endpoint A. That will give us our actual interval. And again, E, our margin of error, will be this formula that we had from above. So let's do an example of this. Let's construct a confidence interval. So we noted in our previous example that a Gallup poll of 1,487 adults show that 43% of respondents have had Facebook pages. The first thing we want to do is find the margin of error that will correspond to being 95% confident. Then we want to build our confidence interval for the population proportion based on that 95% confidence interval. So let's do this. Okay, the size of our sample is 1487. Our point estimate, our sample proportion, is 0.43. That makes Q hat 0.57. Remember, Q hat is my 1 minus P hat value. I want to be 95% confident, which gives me an alpha value of 0.05. To find my z sub alpha over 2, I look at computing the z-score, which gives me an area to the right of 0.025, or again, an area to the left of 1 minus that of 0.9750. We've done that. We've said that my critical value, my z sub alpha over 2, that corresponds to being 95% confident, is 1.96. So we can go ahead and compute part A, our margin of error. E is going to be z sub alpha over 2 times the square root of p hat, q hat over n, which will be 1.96 times the square root of 0.43 times 0.57 divided by 1487. And again, all of that is in the square root. The only thing outside of the square root is my z-score. If I compute that, I'll get 0.025. And typically, we round to 3 decimal places. That is part A of our solution. To build our confidence interval, we take our point estimate p hat of 0.43 and our margin of error, which we computed to be 0.025. To find our left point, we take our p hat and subtract e from that. So 0.43 minus 0.025, that gives us a value of 0.405. To find our right point, we take p hat and add e to that. So 0.43 plus 0.025, and that gives us a value of 0.455. That tells us our left endpoint of 0.405 is our bound to the left of our population proportion P, which has a bound to the right of 0.455. This is one valid way to write our solution. A second valid way is to actually write it in terms of an interval like we would in an algebra class. Right? Either one of these two is a valid solution for constructing a confidence interval. The next few examples we do will be about going backwards. Given a confidence interval, how can we determine some information about our problem? The first is if we're given the actual confidence interval, we can find both the point estimate and our margin of error. To find my point estimate, I'll take my upper confidence level limit, add it to my lower confidence limit, and divide by 2. If I want to find my margin of error, I'll take that upper confidence level here, in this case, subtract my lower confidence level and divide it by 2. So here's an example. Of 71 subjects, 70% were abstinent from smoking at 8 weeks. We have a 95% confidence interval of 58% to 81%. And so what we're not given is the proportion of people in that study or the margin of error. And so we can use that formula from above, that if I want to find my point estimate, my p hat, I'll take my upper limit of 0.81, add my lower limit of 0.58, and divide by 2. That will give us the point estimate for this problem of 0.695. To compute my margin of error, I'll do the same calculation, except I will subtract. I'll take my upper limit of 0.81 and subtract my lower limit of 0.58, divide that by 2, and get my computed margin of error. These two calculations are less common in a class like this, but nonetheless, we can compute them. One aspect that we may want to solve for is determining the sample size given a margin of error. If we want to design a study, we may want to know how many people we need to poll in order to be so confident with a certain margin of error. And this type of problem is really used in polling design. If we want to be 95% confident and have a small margin of error, how many people must we poll in order to do that? That's really what we're looking for. Again, we have the same variables, the same notation, where P is going to be our population proportion, Q is going to be our sample proportion, Q hat. And in this case, this is what we're going to solve for. This is going to be the number of sample values. And in this case, we're going to be given E, a margin of error, and be given a critical value, Z sub alpha over 2. So let's quick look at the formula for this. This is an unusual case because we actually get two formulas. We could imagine that maybe we do know a point estimate for p hat, and maybe we're designing a study that has never been done before, and we have no estimate, no way of knowing what a sample proportion may be. If we do know an estimate for p hat, we get the first value for n. We get n is our critical value squared times p hat times q hat, all divided by our margin of error squared. If we get no estimate for p hat, then we get a very similar formula, but instead of a p hat and q hat, we replace that with 0.25. Very often we talk about how many decimal places does one number need to be rounded to. This is a very easy case in this example because we're computing the number of people that need to be polled. We cannot poll a decimal number of people. So anytime n is a decimal, we automatically will round up to the next whole number. For example, if you compute this and get a value of 1067.11, right? There's no way to poll 0.11 people. We will just automatically round up to 1068. Let's look at an example of this. We want to conduct a study of the percentage of adults that make online purchases. And we want to do this so that we are 95% confident that the sample percentage is within an error by no more than 3 percentage points. And we're going to do this formula two ways. Once, assuming that we know that 80% of adults make online purchases, and once, by assuming we have no information about the population proportion. This will be knowing a p hat value. This will be knowing no p hat value. So let's go on and look at these examples. All right, in this first part, we're assuming we have a point estimate of 0.80. That means I have a q hat value of 0.2. We also want to be 95% confident. That means we have an alpha value of 0.05 and an alpha over 2 level of 0.025. Again, that will give us a z-score, as we've seen before, of 1.96. What we're told is we want to be 3 percentage points within. However, our margin of error should not deal with percentage points, it should deal with a parameter or a proportion. So E is going to equal 0.03. So if I look at my formula, N is equal to Z sub alpha over 2 squared times P hat times Q hat all over E squared, I'll compute 1.96 squared times 0.8 times 0.2, all divided by 0.03 squared. If I compute that, I'll get 682.95. And again, I want to round this up. So N, the number of people I must sample, is 683. If I want to solve part B, I use the same z-score of 1.96. My margin of error, again, is 3 percentage points, or a value of 0.03. But now I don't get to assume I have a point estimate. So I get z sub alpha over 2 squared times 0.25, all divided by e squared. I'll get 1.96 squared times 0.25, all divided by 0.03 squared. If I compute that, I'll get 1067.11. And again, I can't have 0.11 people surveyed, so I automatically round that up to 1068. That is the sample I would need if I have no information about a point estimate. That concludes the information for section 7.1. Hopefully you found this informative. I will talk to you next time.